Welcome back again to the channel. On this video we are going to discuss two problems from Geometry in Figures, problem 1.3 and 1.4. But we will reverse the order. So we will do 1.4 first and then the next one is 1.3. So 1.4 is exactly what we usually call as the inscribed angle theorem, right? So it says that if we have an arc, let's say here, and then we have an angle facing that arc, right? Then the measure of that angle is half of the central angle. The central angle is the angle facing the same arc but connected to the center of the circle, right? So okay, we are going to prove this by considering three different cases. So the first case is if the center of the circle is on the triangle. So we have three vertices. That three vertices form a triangle. So that the center is on the triangle. Okay. In this situation, what do we have? So connect or consider the central angle from central angle in front of that arc, right? So if we call this angle to be twice of alpha, then this guy will be the supplementary of that angle, which means that this angle add up to 180 degrees. Therefore, this guy is 180 degrees minus twice alpha. But notice that these two legs are of equal length. Why is that? Because both of them are exactly the radius of the circle. So consequently, these two angles must be equal as well. But remember that the three angles add up to 180 degrees. So then these two angles add up to twice of alpha, but since both of them are equal, therefore they must be alpha. In particular, that inscribed angle is half of that central angle. So we just prove the inscribed angle theorem in the case where the center of the circle is on the triangle. The next one, we will consider the situation or the case where the center of the circle is inside the triangle. Something like this, okay? So what do we do in this situation? We will create a segment passing through the center of the circle. If we call this as twice of beta, and this is twice of gamma, according to the first case, notice that this one is the central angle correspond to that arc, and that one is the inscribed angle corresponds to the same arc. So therefore, according to the first case, this must be beta. Similarly, we have this inscribed angle and that central angle which fits into this situation where the center of the circle is on the triangle. So if we call this as twice of gamma, then that one will be gamma. So then the original inscribed angle is beta plus gamma, which is exactly half of the original central angle, which is twice of beta plus gamma. So again, the result is still true whenever the center of the circle is inside the triangle. So what is the last case? So here the center is on the triangle, inside the triangle. So the last case should be outside the triangle. So that's the center and that's the inscribed angle. The center is outside the triangle. Okay? So what do we do in this situation? Create another segment so that the center of the circle is inside this triangle and also inside of that triangle. Then we can fall back to the second case, right? So according to the second case, if we look at this central angle and if we call this as twice of beta, then according to what? According to the second case, this inscribed angle must be right, beta. Okay. Now again, if you look at this triangle, then where is the central angle? The central angle is exactly this. So let's call that central angle as twice of gamma. Then according to the second case, the inscribed angle corresponds to that central angle, which is, which one? This one. That's gonna be gamma, right? So then the original inscribed angle that we want to know is this guy, which is exactly gamma minus beta. But what is the central angle correspond to that inscribed angle? This one. And this central angle is nothing but twice of gamma minus twice of beta, which is twice of that. So again, in this situation, the inscribed angle theorem still holds true, right? So therefore, it is true for all cases. Okay? Now for 1.4, 1.3, we have the following situation. We would like to show that if we have an arc, no matter how we draw the inscribed angle, the value of that angle or the measure of that angle must be equal. But that's kind of obvious. Why? Because according to the inscribed angle that we have just shown, this angle is exactly half of that central angle. And that angle is also exactly half of the same central angle. So since these two angles are exactly half of the same central angle, let's call that central angle as twice of alpha, then this guy is alpha and that guy is also alpha. Therefore, any inscribed angle facing the same arc must be of equal measure. Okay, so I think that's all for now. Thank you for watching. See you again on the next video. Bye-bye.